is Dr. N. Amuthipriya, Associate Professor, Tripoli Rohini College of Engineering and Technology, Palkulam. I am here to discuss about the Transmission and Distribution course of Regulation 2021. The first unit covers the structure of power system and the inductance parameters and capacitance parameters along with the skin effect, proximity effect, etc. In this lecture, we will discuss about the structure of power system and the inductance parameters of single and double circuits. Regarding the structure of power system, it consists of three main parts, namely generation, transmission and distribution. While considering the generation side, each country and each generating station generates at an voltage which is reliable for their power system operation. So the voltage value may vary with respect to generating stations. Here we are generating the pictorial representation depicts the generation of 11 kV, and this power plant may be a thermal power plant or a hydro power plant or wind turbine or a solar PV panel or whatever may be the case. The generating station, it generates with the help of the resources present to it, and using turbines, etc. we generate the electricity, and this generated electricity is normally at the range of 11 kV, 33 kV, etc. Next, from the generating station, the electricity is then transmitted and then distributed to the consumers. While transmitting, it has to be transmitted at a higher voltage in order to reduce the I2R losses, the copper losses. So it is an immediate effect to reduce the current so that I2R losses also get reduced. In order to reduce the value of the current, the voltage is being stepped up to high values, and this is possible only with the help of step-up transformers. So from the generating station, the electricity is initially stepped up using a step-up transformer from 11 kV to 220 kV, and this case may be from 33 kV to 132 kV, etc. There are different cases. This primary transmission is very essential because it takes place for a longer distances, hundreds of kilometers, and this transmission will not be disturbed by any tappings from it. That is, no consumers are being directly connected with the primary transmission. And from this primary transmission, the primary transmission ends at a receiving station which is being present at the outskirts of the city, where much more households are not being there. That's the receiving station place. It is a transmission substation. There the electricity voltage, the electric voltage is being stepped down from 220 kilovolt to 33 kilovolt, because after the receiving station, the electricity is then transmitted at a secondary level, not at the primary level. It is a secondary level of transmission. There also we are not going to tap any electricity. It is not being fed to the consumers. So it is 100%. It's a transmission. So this secondary transmission ends at the substation, which we normally call as electricity boards, EBs. There the electricity is then further stepped down. It may be stepped down from 33 kV to 11 kV or 6.6 kV, etc. Here we use a step down transformer. And after that we go for the primary distribution. Why we call it as distribution here? We are not being directly, it is the electricity is further being transmitted to the transformer which is present near the households, but it is not distributed here, isn't it? Not like that. Bulk factories, industries, large scale industries which have their own substations, who have step down transformers within their premises, what they do is they get the 11 kV voltage or 6.6 kV voltage supply from the substation directly, the electricity board directly to their premises. where they step down the voltage according to their needs. Here what we are going to do is the distribution substation which is present nearer to our house is that the 11 kV or 6.6 kV is then stepped down only to 400 volt and 230 volt, not any other voltages. So the large scale industries or factories which are meant to have a different value of voltage, they tap the 6.6 kV. This is the thing. Till which we have feeders. The feeders are not being tapped. This is the condition. And after that, from the distribution substation, the voltage which is being sent to the consumers, that may be a 3-phase one or a single phase one. For 3-phase consumers, 400 volt is being supplied, and for single phase consumer 230 volt is being supplied. So in the secondary distribution side, we have service mains which are being tapped. This is a short form of the distribution, where we have from the distribution substations we have feeders which are not being tapped, and the service mains being tapped. While considering the parameters, we have three main parameters: resistance, inductance and capacitance. Obviously, resistance is an inbuilt parameter in each and every transmission line. We need not add the resistance. The transmission line itself will have some resistance due to the material nature, and the resistance value R is equal to rho L by A. Obviously, it is depending upon the temperature and its coefficients. The resistance value between two temperature differences may be R2 is equal to R1 into 1 plus alpha 1 T2 minus T1, where alpha 1 is equal to alpha 0 divided by 1 plus alpha 0 into T1. Next, let us consider about the inductance. Let us first see about the case of single phase transmission line. Here we have two conductors. One is a go conductor and the other one is a return conductor. Both the conductors are of radius R and they are separated by a distance D. Initially, let us find out the flux linkage of the conductor A, from which we can calculate the inductance of conductor A. First, let us have the flux linkage with the conductor A due to its own current, that is current IA. So it is mu naught IA by 2 pi into 1 by 4 plus integral of R into infinity dx by x. This is what is the flux linkage formula which we have derived. And next, due to current B, the value has been changed to IA. We are replacing by IB, and this is due to self-resistance. Self-inductance. And this case will be from D to infinity. D is nothing but the distance between IA and IB. Since we have two different fluxes, both these fluxes are being added. We are integrating, and also we know IA plus IB is equal to 0, with which we are substituting the value and finally getting psi A value, from which the inductance LA is equal to psi A by IA can be calculated. If it is a loop inductance, obviously it is 2 into LA, because we are having a go conductor and a return conductor. So this is what is the case of single phase transmission line. Next, let us see about the 3-phase transmission line. Normally, if it is a 3-phase transmission line, then we have 3 different distances. That may be a case, or if it is of symmetrical spacing, all the 3 distances will be the same. So let us consider conductor A. It has been affected by its own current, the current IB and the current IC. Those flux linkages are being given in this equation. We have to add all the 3. We have psi A. As we know, IA plus IB plus IC is equal to 0. Let us substitute the same formula over there, and finally we will be getting the value for LA. This is the case for symmetrical spacing. And if it is for symmetrical spacing, obviously we know the current will be a vector, because they are being separated with 120 degree spacing. So I mean the difference, phase difference. So obviously when considering IA and IB, it is of minus 120 degrees, and if it is IC, it is 120 degrees with respect to IA. And next we have to add all the 3 values. We will be having psi A and LA value, LB value, LC value. Since 3 inductances are there, we have to take the average of it, and obviously we will be getting the inductance of each line conductor to be the equation. Thank you.